We're in chapter 18, which is about magnetic fields. Now, last time we talked about how to calculate a cross product mathematically, and we've also been discussing how to know the direction of the cross products using the right-hand rule. We discussed the difference between electron current and conventional current. From now on in the course, when we say current, we're just going to mean conventional current. Okay, so current means conventional current. Although inside of a real material, the current is actually carried by negatively charged electrons, right? All electrons are negatively charged. So the current, the current being carried by electrons is carried by negatively charged particles. Conventional current is where we pretend. We pretend that the current is actually carried by positively charged particles moving in the opposite direction. Partly that's just convention, and partly it makes the math easier because there's one less minus sign to worry about. So we calculated the electron current and compared it to the conventional current. And of course, our conventional current isn't quite true. It's just that it's useful because it's the convention, and it's also easier to track positive charges than negative charges. We talked about the Biot-Savart law in a wire. The Biot-Savart law was, here it is. The Biot-Savart law for a point charge we discussed first, which is where we have a point charge that's moving with respect to you. Okay, so it's got a velocity with respect to you, the observer. And then to find out the direction of the magnetic field that you observe due to that moving charged particle, we take that V cross R, where R is a vector that goes from the point charge to you. R points to me, right? And so that tells us the direction. We generalize that to a little segment of current wire, okay, current carrying wire. So this is a little segment, delta L, of a current carrying wire. And so the Biot-Savart law in that case became delta B equals mu naught over 4 pi. I delta L cross R hat over R squared. And so the only difference between these two is that the QV of the point charge becomes I delta L in the case of the current carrying wire. Do you have any questions about that? Okay? All right, so today we will build that up then to not just the current and a little piece of the wire, but we're going to integrate all along a long straight wire to find the total magnetic field that that wire produces. And then we'll apply the same method to a loop of current. So if I take current and run it in a circle, what kind of magnetic field does that produce? I've got parentheses here because having seen the guts of this calculation for the straight wire, I'm not going to show you all the guts of the calculation for the current loop. It's the same method, so I'll show you the steps, but what you should focus on there is just the result. And then we'll talk about a magnetic dipole moment and what that means, compare that to a bar magnet, and we'll see what it is inside of materials that causes magnetism. So first, let's think about the magnetic field of a straight wire. Let's say that I have a wire carrying current, and the current's going to go up. In this case, I have x-axis this way, y-axis goes to the back, and z is straight up. So let me have a current carrying wire pointing straight up. Due to the little segment here, I can calculate the magnetic field over here. I'm going to calculate the magnetic field in the bisecting plane of that wire. Okay? Does this look a little bit like something we did in electrostatics? Okay? We did a long rod in electrostatics, right? So let me remind you first how that went. So in the case of the rod of charge, okay, this is straight out of lecture 5. And we'll use this analogy to feed into how to calculate the magnetic field in the current carrying case. So if I just had the rod of charge, the way this calculation went was we calculated the electric field in the bisecting plane. And the reason we did the bisecting plane is because that was a high symmetry point. It was easier to calculate in the bisecting plane. The method works anywhere in space. It's just that anywhere in space gives you a really yucky looking integral. If you go down to the bisecting plane, it simplifies. Okay? So we went into the bisecting plane, and we saw that what we needed to do was stand at the observation point, calculate the electric field at the observation point due to a chunk of the wire, okay, so due to a chunk of the rod. And we wrote that down explicitly, and then we integrated over all the little pieces of the rod. That was this sum over delta q's, adds up all the charge, and then we converted that into an integral over the length of the wire. That's straight out of lecture 5. What we're going to do today is very similar. So same methodology. It's just that now we're calculating a magnetic field. So I'll again take the bisecting plane of the long wire. Okay? So get in that bisecting plane. Put yourself in the observation point right here. And I'll calculate the magnetic field contribution at this point due just to this little piece of the wire. So step 1, draw a really careful diagram where you know right where the rod is. We've put the rod on the z-axis. I'm going to have an observation point on the x-axis in the bisecting plane. And I want to write down what's the contribution of the magnetic field right there due to a piece of that current carrying wire. So that's step 1. So in doing that, what I like to do first in all these problems, right, first draw the really good diagram, and then after that, write down R. Remember that R points to me. So you imagine yourself at the observation point, and R is a vector that goes from the current element you're considering, from this little chunk up here. It points from that to you. That's where R is. So in my diagram here, R goes from the current element to me at the observation point. R points to me. So now I write down the vector R. It is, according to the diagram, it's got a positive x component. So I write that down. It's got nothing along the y-axis. And in going from here to here, I go a negative amount along the z-axis. So there's a minus z right there. So I wrote that vector down after having drawn the really careful diagram. Now from R, I calculate its magnitude and its direction. So the magnitude of R squared is going to come directly into our equation. So I need R squared, and that's x squared plus z squared. To get R hat, I take R divided by its magnitude. So R is x comma 0 comma minus z, and its magnitude is square root of x squared plus z squared. I like to just write all that stuff out so that then when I go putting it in the equation, it's crystal clear. So now I'm ready to put these things in the equation. The first thing I need in calculating this little piece of magnetic field is I need something called delta L cross R hat. In our case, delta L, okay, so delta L is always parallel to your wire, right? So it's wherever you are in that little wire, look at the direction of the wire. And then delta L points in the direction of the current. So here I've got current pointed up. So delta L is pointed up right there, which means I can write it as delta Z, okay? So in this case, delta L is parallel to delta Z. So I'm going to write this as delta Z cross R hat. So our delta L is delta Z, which in vector notation is 0 comma 0 comma delta Z. So now I need delta Z cross R hat. And that's looking up here at what R hat is. I'll be taking delta Z cross R over its magnitude. And here's how to calculate that. I use determinants to calculate these cross products. So there's the 1 over magnitude of R right here. And to calculate then the cross product of delta Z crossed into R, I write in the first row, I write x hat, y hat, and z hat. In the next row, I write the components of delta Z. That's 0 comma 0 comma delta Z. And in the next row, I write the components of R, which is x, 0, and minus z. And then I take the determinant of that. Now, the way that I think about taking determinants is I think of drawing diagonal lines on this matrix. So if I draw a line diagonally down to the right, then anything I pick up along the way gets multiplied together with a plus sign. So x hat times 0 times minus z gives me 0. So I got nothing there. And then when I go to the next spot, I get y hat times delta z times x. Okay? That gave me this component here, x times delta z in the y hat direction. And then going diagonally down to the right, starting from z hat, I get z hat times 0. Okay, so that one went away. And then the other thing I have to do is go diagonally up and to the right. And those things contribute with a minus sign. So going diagonally up to the right, I'll get an x times a 0. Okay, that term went away. I'll get a 0 times a delta z. Well, that term went away. And I get a minus z times a 0. That term went away. Okay, so the only term that contributed was x delta z in the y hat direction. All right, so that's all together delta z cross r. I'm sorry, cross r hat. Now I should go back and check it, right? So I need to use the right, that was math. And we should always do the math extremely carefully so we always get the right answer. And then do the double check so you know you got the right answer. Do the right-hand rule real quick to make sure that this is in the right direction. So delta z crossed into r hat. According to my diagram, delta z is up. R hat is pointing a little bit down, like that, towards the x-axis. So my thumb points backwards, which is in the y direction here. So I have delta z cross r hat, and then it's pointing in the positive y-axis. So that worked. So that gives me a double check. Helps me know, well, if I had made a mistake, it probably would have shown up there. All right, so now then this is x delta z over square root of x squared plus z squared. In place of the magnitude of r, I wrote square root of x squared plus z squared. All of this is in the y hat direction, as we said, and that is delta z cross r hat. So I'm one step along the way now to calculating this guy. All I've done so far is the delta L cross r hat term in the Biot-Savart law. Do you have any questions so far? Okay, and really to do physics really well, you want to do both of those in parallel. You want to do your diagram really carefully, right? Do the math really carefully, and go back and check it physically with the right-hand rule to make sure you got the right answer. Okay. All right. So here's what we had on the last slide. Delta B is mu naught over 4 pi I delta z cross r hat over x squared plus z squared. We also calculated delta z cross r hat. So now I'm going to plug that in. Okay. And altogether, I'll get a mu naught over 4 pi I. There's a y hat here. There's an x delta z. That's all coming here. And now I need to combine the denominator. I'm going to have x squared plus z squared times square root of x squared plus z squared. So that's a power of 1 here and a power of a half. 1 plus a half gives me altogether 3/2 power down there in the denominator. You OK with that? All right. OK, that's just one piece, right? Now I need to take an integration, right? So this was just the contribution to the magnetic field due to that little bit of wire. I need to sum up the whole length of wire. I'm going to assume now that I have a length of current carrying wire that's L, okay, of length L, and that I'm observing at the midpoint. So I'm going to set the origin at the midpoint of that current carrying wire. So I'm going to take an integral that runs lengthwise. It's going to run from minus L over 2 to positive L over 2. What I'm really doing is I'm integrating the little delta b's that contribute, right? So there'll be a delta b from one piece and a delta b from another piece and so forth. So I have an integral delta b. But in order to take that mathematically, I need to convert it into our x and y coordinates here. And so that becomes integral, right? This stuff up here is now going to become an integral. The delta z is the thing that turns into dz in the integration. So now I have that whole thing integrated dz from minus L over 2 to L over 2. Questions so far? OK. All right, and you all remember how I take integrals, right? At this point, I look it up in Wolfram alpha. OK, but you have to know what's constant and what's changing. So tell me, in this integral, does x change during the integration? No. All right, how do you know that? Are you sure? Yeah. Pardon? Oh, yeah, OK. All right. So the integral is in relation to z. All right. So x is another independent coordinate. So I'm integrating over z. At the same time, while I'm doing this integration, the observation point is not moving. In fact, that's pretty much always true, right? Your observation point should not be moving during these integrations. And the observation point is here. It's a distance x from the rod. So yes, as Ozzy's pointing out, the x doesn't change during the integration, just the z. So observation point x doesn't change during the integration. I look up the integral in order to take it, and I get that the magnetic field there is mu naught over 4 pi I L over x square root of x squared plus L over 2 squared. That's the magnetic field of a long straight wire. And I've put magnitude by here to remind us that it's in that y hat direction at that spot in space. So right here at this spot, a distance x along the x-axis, it points back in the y hat direction. Do you have any questions about that? OK. All right. Let's think about what if I rotate this wire now. Leave the wire right where it is. I'm just going to take the wire and spin it around the z-axis. OK. So if this I clicker represents the wire, I'm just going to turn it around. Does my answer change? No. All right. What if I leave the wire where it is and I rotate my coordinate system around it? I should still get the same physics, right? So that means that anywhere I am that's a particular distance x from the wire, okay, from the midpoint of the wire, I could walk around in a circle on that plane, and I should get the exact same answer. I should always get that if I walked around, if I took a circle in that plane, a distance r, let's say we're distance r now for radius away, then I would find that the field, if I walked counterclockwise, the field was always parallel to the direction I was facing, okay? Because I could rotate the coordinate system, or I could rotate the wire and I'd get the same thing. That's actually equivalent to what's happening up here. What I have here is a bunch of little compasses, okay? And then I have wire here. And then when I turn on the current for the wire, all right, now the compasses all choose which direction they should point based on the magnetic field that they feel. So they're locally feeling a particular magnetic field, all right? And the magnetic field pattern here corresponds to what we just calculated, okay? Do you see how that's working? If I stand, let me focus that a little better for you. All right, so there's teeny tiny compasses all over the place. And if I look at this diagram on the board and this situation here, I can see that basically we were a distance x out, and the magnetic field is pointing back along the y-axis, okay? So the current in this wire must be coming out towards us. So right here, the current is coming up, just like in the diagram on the board. Do you have any questions about that? Yeah? What happens for infinitely long wire? Oh, I'm glad you asked that, because we're going to calculate that in like 2 slides. Sound good? OK. All right. Now, I want you to start thinking about space as filled with teeny tiny compasses. This helps you visualize the magnetic field. So think about anywhere in space, there's a teeny tiny compass like that. And if you zoom into any spot in space with your mind's eye, you should be able to read that compass. And the compass will point in the direction of the total magnetic field there. So if I think then of how this pattern looks all throughout space, it's basically concentric circles, okay? So B is always pointing along. I'm going to turn this off. B is always pointing along circles in this case. So I have current going up, and this is the pattern we see on the board there, and this is the pattern that we calculated. A better way to express this physics is in cylindrical coordinates. I derived it in x, y, z, in Cartesian coordinates. But the problem really is better suited for cylindrical coordinates. So cylindrical coordinates are where I say, OK, there's an axis, a z-axis here. And then anywhere in space, I'll take the shortest distance to the z-axis and call that coordinate r. So r is now just a distance, shortest distance to the z-axis. And then there's this coordinate theta, which tells you where you are around the circle. Okay? That's cylindrical coordinates. And this problem lends itself to cylindrical coordinates. So as we said, I could walk in a circle of radius r around this thing. And if I walk in that direction of the magnetic field, then this math here in cylindrical coordinates represents that idea. I've got a theta hat there. Okay? So theta hat just says, well, what's the direction that the angle will go around? All right? That's the direction of the magnetic field. So the direction of the magnetic field lines here are always pointing in the theta hat direction. I've taken our result from Cartesian coordinates, and I've switched out x for r, where r now represents the shortest distance to the z-axis. Do you have any questions about how that happened? OK? So this is like another right-hand rule, basically. So I have here, did you guys see my video last night to help you do the homework? OK? I thought we came up with that in office hours, how to make your own little magnetic field visualizer. So here I have a bigger version, OK? And I will point out that it's the end of the summer, so pool noodles are on sale right now. If you want your own for your dorm room, get your own little magnetic field, big magnetic field visualizer. So I have your current, OK? Remember, current means conventional current. So I wrote that too, just in case I get confused. All right? So this is current. And here I have a shape of a magnetic field. It could either be going clockwise or counterclockwise. So according to that diagram there, how should I poke this current into the magnetic field? Should it be this way? Or should it be the red side? Red side, OK. So all right, so just to double check, this is, if I have current pointing up like the diagram, then this is going to have magnetic field going in that direction, which is the same as our diagram up there. Okay? So there is another right-hand rule going on here, which is that if current is going this direction, I can point my thumb along the direction of current, and then my fingers curl in the direction of the magnetic field. Okay? And it works up here too, even though that's the black side. The current is pointing this direction, and I curl my fingers in the direction of the magnetic field. Okay? And you'll notice that in going from the red side here has magnetic field this way, the black side has the magnetic field in the exact same direction, right? It's this direction on both sides. Okay? So when the current's facing away from you, magnetic field goes clockwise or counterclockwise? Yep. And when the current's facing towards you, counterclockwise, all right? Now, that's so important that I don't want you to forget it. Don't fall off. Okay. So I have a little, little story to tell you while I draw something here. Is anybody here a morning person? Anybody? Morning? You're not going to get hurt, by the way. I'm not asking for volunteers to come up or anything like that. Just curious if anybody's a morning person. I am not a morning person, so I don't like my alarm clock. I'm drawing a clock face, by the way. I don't like my alarm clock in the morning. The alarm clock goes off, and although I'm really excited to get up and come teach you physics, at the time, I'm not happy to hear the alarm clock, right? So there's my alarm clock in the morning. And not being a morning person, I kind of don't like my alarm clock, okay? So this is kind of how I feel in the morning. Did anybody else feel like this when they hear the alarm go off? Okay, all right. I want you to take all that rage from the morning. I'm going to step back from the front row. They're getting nervous, okay? Take all that rage from the morning when your alarm clock is going beep, 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 wah, 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 or whatever it does. Beep-do, 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 if you like, Minions. Okay, and just do this to it. All right? Pretend that was in the center, okay? Now, see that rage is going to help you remember the right-hand rule, right? Because the knife represents the direction of current, and then the magnetic field goes clockwise around that. All right? So just imagine yourself stabbing your alarm clock in the morning. Current, you're never going to forget this now, right? Okay. Current goes this way. Magnetic field goes that way, okay? And no one's going to sit in the front row again, I bet. Okay. No students were harmed in the making of this lecture. All right, good. Any questions about that? Okay, so this idea here tells you what that theta hat means. All right, now you asked the great question of what happens if we have an infinitely long wire. And there's two ways to think about that. You can either think about the wire getting infinitely long, or we can think about the observation point getting infinitely close to the wire. So either way. And so here's the equation we had. We had that the magnetic field coming off of a long straight wire is mu naught over 4 pi IL over r, square root of r squared plus L squared, no, plus L over 2 squared. And all of that is in the theta hat direction. Now, very close to the wire, all right, the cylindrical coordinates are about the shortest distance to the z-axis. So align your current with the z-axis. And at an observation point here, the shortest distance to the wire is this. That's r. If it could be down here, the shortest distance to the wire is r. Okay? Now, so that's the r I'm talking about. Very close to the wire, r becomes very small compared to the length of the wire. All right? So remember how to do approximations. When you're doing approximations, you want to find two length scales. So here I have r. It's going to be small. And I have L. It's going to be large. Right? So you find your two length scales, one big, one small. Pretend they're money, right? Pretend the big length scale is billions of dollars, and the small length scale is like pennies, and pretend you're the billionaire, right? Do you care about the pennies if you're a billionaire? Probably not, right? You get, you're like walking along, you're like, I'm a billionaire, you see pennies on the ground, you don't pick them up, you don't care, you're a billionaire, right? So then you look in the equation for places where pennies are added to billions of dollars. If they're multiplied, you can't make an approximation, right? Because $1 billion times a very small number matters to you, right? But $1 billion plus pennies doesn't matter to you. So here's the $1 billion, L over 2. And here's the pennies, which is the r term. So I neglect the r term and say that altogether, square root of r squared plus L over 2 squared is approximately equal to L over 2, if L is really large, okay? And then very close to the wire, this is what the equation looks like. So then that becomes that the magnetic field is mu naught over 4 pi IL over r times L over 2 in the theta hat direction, which is altogether mu naught over 4 pi 2I over r in the theta hat direction, close to the wire, or for an infinitely long wire. Do you have any questions about that? And here's the question. I have two current carrying wires. This one is carrying current to the left, and this one is carrying current to the left. And assume they're carrying the same current. And at an observation point directly in the middle of those two wires, what kind of magnetic field do you observe? Okay, what's the direction of the magnetic field at that location? Okay, what are you thinking? What do we need to take into account here? What's a line of reasoning that we need to consider for this problem? And it's always okay to tell me your neighbor's line of reasoning. That's okay. Oh, yeah. Okay, so he's arguing that, I'll repeat this for the people in the back, tell me if I get it right. So he's saying the upper wire, actually I can use the pool noodle. All right, so he's saying the upper wire has the current going this way. Therefore, the magnetic field is coming out towards you. And then the lower wire has the current going that way, but at the observation point, the magnetic field's going back. And those are two different directions. So the one up top has field towards you. The one on the bottom has field away from you. And those contributions tend to cancel. And in the case where the currents are exactly the same and we're measuring a midpoint, they exactly cancel. Now I want you to do it for the other case. All right, so now I have conventional current going to the left up top and going to the right on the bottom. What's a line of reasoning we need to consider? And again, we're much more interested in lines of reasoning than in the end answer, right? Because the thing you need to get to the end answer is actually the line of reasoning. So. Yeah, right here. Okay. Okay, so you said by symmetry, whatever fields they're producing are going to be in the same direction at the x point. So you just calculate the top one. And the top one has current going this way and field pointing back towards you. All right. Other lines of reasoning we need to tangle out? Got it? You good? Okay. All right. And of course, you should make your own magnetic field visualizer Tron thingamajig to do your homework. That's its official name. We're going to patent that, right? So the top guy has current going this direction, and coming out towards you is this magnetic field, right? And then the bottom guy has the current going the other direction, and it still has current coming out, field coming out towards you. So in this case, the fields add, and they're all coming out towards you, which in the diagram is the positive z-axis. All right, now that we've got that in our heads, that when I think about the magnetic field that a current carrying wire makes, I want to put my thumb along the direction of the current. My fingers curl in the direction of the magnetic field. Okay? Or you can always think of stabbing your alarm clock. Okay, when I stab my alarm clock in the morning, that's like current going into my alarm clock. And then the magnetic field is like the clockwise direction on the clock. Now we're ready to think about another geometry. So let's have a current loop. Let's have a loop of current. So I have a loop of wire here. I'm going to run current this direction. And I want to think about, well, what kind of magnetic field pattern does this make? All right? What we're going to make, by the way, is an electromagnet. When I turn the current on, I'm going to get a magnetic field. And when I turn it off, I won't have the magnetic field. So I can use this Biot-Savart law for current in a wire in order to calculate the magnetic field of the loop of wire here. And again, I'm going to stick to a high symmetry point. We stick to the high symmetry points to do the actual calculations because they're easier to calculate, right? The same principles will apply everywhere in space, and you'll get a complicated formula in the rest of space. So I'd like to orient this loop of wire along the z-axis. I'll take an observation point on the z-axis. So let's sit right here on the z-axis, have the current going this direction. And I need to think about which direction does the magnetic field go in right there on the z-axis. So the thing I'm going to do is do the right-hand rule, right? So I have delta L up here at the top, delta L, and then I need to cross that into R, which comes now pointing along towards the z-axis. And then that gives me, can't quite get it right, can I? So delta L crossed into R points up in this direction. There's the delta B pointing up. Now I need to think about, that's just the contribution from that top piece of the wire. I need to think about what happens when I sum up all the contributions all along the entire loop, all right? And as I do that, all right, this piece from the top of the wire gives me something that's pointing a little bit up. As I sum around the wire, I'm going to get contributions that go like this around the z-axis. All the components that are off the z-axis will cancel each other as I go around. And so I just get something that's net in the z direction, all right? So the net magnetic field along the axis is just on the z-axis, all right? And this procedure that we always use, we write down now the magnetic field due to one piece. And in this case, the magnetic field then due to one piece is this. Now, that's lots of math, okay? This is a step, this is tons of math go in between this. Write delta BZ due to one piece and this answer here, okay? It's just that it's the same method that I've showed you a few times, so I'm not going to show you all the little steps this time. In fact, we're doing something more like this. I think you should be more specific here in step 2. I just want you to remember the method, right? How we get it. And then I'll take this guy and integrate to find the total B. So when I integrate around that guy, lots of math happens down here. And here's the answer that I want you to take home. Okay? So is the method clear? Draw the careful diagram. Look at the observation point. Use the Biot-Savart law to calculate the magnetic field due to one piece. Integrate all around the current. And then that gets you the total magnetic field. That method gets you this answer. So it's the same method we used before for the long straight wire. And now what I want you to focus on is the answer itself. So here's the magnetic field then due to a loop of wire on the axis. It has a mu naught over 4 pi in front to get the units right. There's I, which is the current in the wire. R squared 2 pi over R squared plus Z squared to the 3/2. R is talking about the radius of the loop of wire. So that's how big this wire is. Z is how far away I am along the axis of the loop of wire. So if I center the loop of wire on the origin and have its axis coincide with the z-axis, this Z is how far away I am from the loop of wire. Okay? So that's the answer. And it's a lot of math to get from here to there, which we're skipping. Now, I'm going to double check real quick and make sure the units are right. The units here, mu naught over 4 pi has units of Tesla meters per amps. This stuff on the right has amps meters squared. That's amps meters squared. And in the denominator here, I have meters squared to the 3/2. Okay? So does all of that work out? All right, I can take this 2 times the 3/2. Gives me altogether a 3. So I have 3 powers of meters that cancel these 2 plus that power of meters. So that works. Amps cancels amps. And I'm left with Tesla. So the units work. Check. All right? And then I should check and make sure it fits the right-hand rule, right? So I have a loop of wire with current going in that direction. And let me orient my thumb along the direction of the current, okay? When I orient my thumb along the direction of the current, so let's be at the top. Think from the top of the wire here. The current's coming towards you, so field should be poking this direction along the z-axis, right? And I can orient my thumb over here on this side of the wire. Current's pointing down, but magnetic field's still poking in the center, and so on. All the way around, I'll get that the magnetic field points along the z-axis the whole time. Do you have any questions about that? Okay, so the direction is working out. Yeah, question here. What is Z in the equation? Z is distance along the z-axis. This should have been labeled. So this diagram here, this axis coming along this direction is the z-axis. I'm sorry, I should have labeled that. So I'll post that online. I'll post that correction. This is the z-axis here. Does that help? Yes. So if I take the current loop and put the current loop so that its center is at the origin of the coordinate system, and then for any loop there's an axis for it. So I'm putting that axis along the z-axis. So to show you in terms of, let's see. here's another paper plate. So if I say that current is going along the rim of this guy, right? Okay, pretend I'm a better artist than that. So to match the diagram, right, current is going along the rim of this guy, then the z-axis points straight out of the middle, like that. Okay, so z is going to be, this equation is for on that z-axis and how far am I from the ring, okay? And all that direction, the magnetic field points this way, and then it points that way as well. Thanks for asking. The diagram should have been clearer. I'll post a correction. Do you have any more questions about that? Okay. All right, so here, this might make it clearer too. If we think in terms of that loop of wire, anywhere along the loop of wire, you can orient your thumb on the direction of current, and then your fingers poke in the direction of the magnetic field. So in the interior of the circle here, I've got magnetic field coming out towards you. All right? If you like, you can turn that into yet another right-hand rule, which is over here, which is where I take the loop of current, and now it's a different right-hand rule. If I put my fingers in the direction of the current, in the middle of the circle, then my thumb points in the direction of magnetic field, in the middle. Okay? And then outside of that, it's pointing in the other direction. Do you have any questions about how that guy went? Okay? All right, the overall shape of this thing. So here's a current-carrying wire, all right? The overall shape of it is that there's a magnetic field that on the z-axis points all along the z-axis and then loops back around in space, right? Ultimately, we have current coming out here, and I need to think about the right-hand rule up there. Think about current going into the board at this spot, and then magnetic field lines wrap around that. And now fill all of space with those patterns, and I get this where the magnetic field comes out here, comes back around, and back in the other side. So this shape actually is very similar to the shape we had for an electric dipole. Okay, when we talked about an electric dipole, that's a positive charge here and a negative charge here, and the electric field comes out of the positive side, wraps back around into the negative side. At least far away from it, not in the middle. In the middle it's different, but far away from it, the fields look very similar. Now, if I think of the current loop, and now let me take an observation point far away from the current loop. So here's our equation for on the axis of the current loop. It's mu naught over 4 pi times 2 pi r squared I over r squared plus z squared to the 3/2. By the way, what happens in that top equation? So let me take that top equation, and let me put in a negative z. What happens to the negative z in there? Yeah, the minus sign goes away, right? Because I have a minus z times a minus c. So in fact, the arrows are telling you something about that as well, right? The arrows are showing you that the magnetic field is always pointing in the positive z direction. And the equation represents that as well. All right. Now, far from the loop, if I take z as much, much greater than r, okay, remember how approximations go. You look for two different lengths of different sizes. One length is large, the other one's small. I call the large length like billions of dollars. I call the small length like pennies, and then I look for a place where they're added together. Here's where they're added together. I have r squared plus z squared to the 3/2. So in that case, if the z is billions of dollars and the r is pennies, I'm a billionaire, so I don't care about the pennies. I cross them off, and I get altogether z squared to the 3/2, which is altogether z cubed. Okay? So that gives us the magnetic field along the axis far from the loop. Here, I've taken the z and just measured it in terms of little r as distance from the loop itself. Do you have any questions about that? Okay? All right. So basically, far from any dipole, whether it's a magnetic dipole or whether it's an electric dipole, when you're far from the dipole, the strength of the field, the magnitude of the field, falls off like 1 over r cubed. Whether it was an electric dipole or whether it was this thing here, which is actually a magnetic dipole. This is the same field configuration that you actually have for a bar magnet as well. So if I have a bar magnet, which is a magnetic dipole, this is not labeled so that you can see it very well, but this is north and this is south, the field configuration coming out of a bar magnet does the exact same thing as this current loop, all right, when you look far enough away. So if I have a bar magnet here and I measure its field far away, it's going to look like that. If I replaced this with a current loop and I went far away and measured the field, it would look exactly the same. All right? So they both fall off like 1 over r cubed. Now, one of the things I'd like to know, though, is why does this bar magnet act like a current loop? All right? It probably means that inside the bar magnet, there's little current loops. All right? And in fact, that's the case. There are little current loops inside here. So let me think about where they might be. A current loop makes an electromagnet, right? So I turn on the current and I get an electromagnet. I turn off the current and the magnetic field is gone. All right? So in fact, it turns out that electrons are doing something very similar inside this piece of material. Okay? So if I think deep inside the material, okay, put yourself deep inside, think in terms of what the electrons are doing inside. Electrons orbit their atoms, all right? As they orbit their atoms, they sometimes make motions that are very much like a little current loop. And when they do that, they're making a little electromagnet. Now, in most materials, those little electromagnets all cancel out in the material. In a permanent magnet, though, what's going on is that every single little electric current loop has a line, and that's what made this thing a permanent magnet. All the little current loops lined up in the same direction, and then all their magnetic fields add up and add up and add up, right? And then that gives me this total permanent magnet, all right? Now, there's one other thing that's going on inside of a bar magnet, which is that the electrons actually spin on their axis, and that's kind of weird. So think, in this case, think in terms of an analogy with what the Earth does in the solar system, right? So the Earth goes around the sun, all right, and that's like the electron orbiting its atom and making that big current loop. That's like the big current loop. But the Earth also spins on its axis, all right? Now, if I think of the Earth as being a big ball of charge, then if it were spinning on its axis and it's a big ball of charge, then that's also creating a little current loop there as it spins on its axis. Would you believe that electrons actually act like that? Okay? So electrons have a charge, and it looks as though every single electron in the universe is spinning on its axis. The weird thing about that is that as far as we can tell, electrons don't have any size. They have 0 radius. So that'll wig you out, but it's quantum mechanics, okay? All right? So there's 2 reasons that electrons act like little electromagnets. When they all align in a material, that gives you a permanent magnet, okay? All right, we're done for today. I'll see you guys next week. All right, I want you to take all that rage from the morning. I'm going to step back from the front row. They're getting nervous, okay? And just do this to it. No students were harmed in the making of this lecture.